All right, let's dive right into this explainer. Today, we're looking at a truly fascinating new research paper published by Sungyan Lee, Sean McLeish, Tom Goldstein, and Julia Fonte. The paper is titled Language Models Need Sleep, and honestly, it proposes something that sounds straight out of science fiction, giving artificial intelligence a core biological necessity. We're going to explore exactly how engineering a sleep-like phase for large language models might literally be the key to unlocking their ability to handle massive, complex tasks without, just crashing under their own weight. This quote directly from the paper's abstract perfectly frames the foundational problem we're tackling today. See, we want our AI models to read entire books, analyze thousands of lines of code, and perform what researchers call long-horizon tasks. But standard transformer models rely on an attention mechanism to keep track of all that information. And the issue? As the context length grows, this mechanism scales terribly. It becomes incredibly computationally expensive. For an everyday user, this is exactly why an AI seemingly forgets the beginning of your conversation or starts hallucinating weird details after analyzing a massive document. Real quick, here is our roadmap for today. First, the long context problem. Second, how AI sleep works. Third, shifting computation offline. Fourth, putting sleep to the test. And finally, more sleep, deeper reasoning. Starting off with Section 1, the long context problem, or when working memory gets overwhelmed. So the absolutely crucial point here is understanding the key value cache. You can basically think of this as the AI's short-term active working memory. When you're feeding a standard language model an enormous amount of data, let's say a massive legal document you want summarized, it stores the recent context right here in this key value cache, so it can quickly refer back to it and predict the next word. But just like a human brain getting completely bogged down and fatigued at the end of a long information-heavy day, this cache simply cannot scale efficiently. It fills up, it bogs down the entire system, and the AI effectively hits a wall. Moving to Section 2, let's look at how AI sleep actually works through a consolidation mechanism. Now, what's really fascinating here is the introduction of state space model, or SSM blocks, along with something called fast waits. If the key value cache is that overwhelmed short-term memory we just talked about, these SSM blocks act as deeper, persistent storage. The researchers designed a brilliant consolidation mechanism where the model can take all that jumbled, heavy context from the short-term cache and convert it into these persistent fast waits. It's essentially mimicking the exact way human brains consolidate short-term memories into long-term knowledge overnight. So how does the model actually sleep? Well, the process happens in 3 precise chronological steps. Step 1. The model periodically converts its recent context into those persistent fast waits. Step 2. Because the information is now safely stored away, the model can safely clear out that overwhelmed key value cache. It just wipes the slate clean. And Step 3. During this sleep phase, the model updates the weights in its SSM blocks through what the researchers call a learned local rule. It's effectively organizing its thoughts, right? Resetting its short-term memory capacity while securely retaining the vital info it just learned. Section 3. Shifting computation offline, a tale of two states. This whole design creates a brilliant architectural division of labor. During wake time, which is when the model is actively doing inference, answering your prompts, generating text, it operates with high-speed, low-latency prediction. It's fast and snappy specifically because its short-term memory isn't bogged down anymore. Then we have sleep time. This is a dedicated period of consolidation where the model shifts the heavy computation entirely offline. It performs offline recurrent passes over the accumulated context. By separating these two states, the model successfully handles massive amounts of information without sacrificing a single ounce of its reaction speed when interacting with you. All right, Section 4, putting sleep to the test, and what turned out to be a real David versus Goliath result. When the team actually put this to the test, the outcome was wild. The researchers tested their method on a variety of really demanding tasks. First, controlled synthetic tasks, specifically cellular automata and multi-hop graph retrieval. Then they moved to a highly complex, realistic math reasoning task. And get this, a regular transformer model completely fails on these long-horizon tasks. Even modern SSM-attention hybrid models fail. But the sleeping model, it succeeds across the board. The consolidation mechanism literally allows it to navigate complex, multi-step logic that flat-out breaks traditional architectures. No contest. Bringing us to our final point, Section 5, more sleep, deeper reasoning. In this research, the authors use the variable n to represent the number of offline recurrent passes the model takes over its context. So essentially, n is the AI's sleep duration. You can program the model to take just a few passes, like a quick 20-minute power nap, or many passes, kind of like a full 8 hours of deep REM sleep. So what actually happens when you increase N? Well, the researchers found something incredible. Giving the model more sleep directly correlates with a significantly increased capacity for complex, deep mathematical and logical thought. The more recurrent passes it takes offline to update its fast weights, the better it does when it wakes up. But here is the real kicker. The absolute largest performance gains from longer sleep aren't found on simple, everyday tasks. They are observed on the absolute most difficult examples that require deeper reasoning. As we wrap up this explainer, I want to leave you with a pretty provocative thought. We've spent decades trying to build artificial intelligence using purely synthetic mathematical paradigms. But here we have a major breakthrough in long context reasoning achieved by mimicking a fundamental biological process, sleep. The lines between human biology and artificial architecture are beginning to blur in ways we frankly never expected. If sleep is required for deep artificial reasoning, what other biological necessities might hold the key to the next generation of AI? It's wild to think about. Thanks so much for joining me for this explainer, and I highly encourage you to go read the full paper from Sungyeon Lee and the rest of the team.